Welcome to the session Strength of Material or Mechanics of Solids or Mechanics of Materials. So here this is a problems which is about varying sections which carries different loadings for different sections. So again here going to apply principle of superpositions, and here varying cross section is given with different loading conditions. So here how to determine the forces or loads for different sections, how we are going to decide that which section having how much loads. If this load is not very clear, then how we are going to determine this? Let us see. So this is a problem containing three different sections, and at the one end it's carrying 40 kilonewton load. At the section at the face V it's carrying 30 kilonewton load. At face C is carrying load P. At D is carrying a tensile load 70 kilonewtons. For section 1, diameter is given as 30 mm. For section 2, diameter is given as 60 mm. And for section 3, diameter is given as 40 mm. So as this is a circular cross-sectional member, so how we are going to decide the loads for a particular sections, that we'll see. Then we'll determine the total elongation due to the application of load for this solid member. Here length is given for section 1 600 mm, for section 2 800 mm, section 3 900 mm. So how we are going to proceed this? Here calculation of loads on the section 1 to 3. First our job is to calculate the loads applied on the particular sections. First of all, we will take a section 1. Section 1 at the left end is carrying 40 kilonewton tensile load. So at the left end, because we are starting from first section, so at the left end is carrying 40 kilonewton load. So at the far end at B it will carry 40 kilonewton load. Then this member will be under equilibrium conditions. So that's why, and this is force is applying outwards from the members, so this will be treated as tensile load or tensile force. So how the left of the sections carrying 40 kilonewton load, left of the section carrying a 40 kilonewton of load. So to maintain the section equilibrium, same load will be applied on the right side. So same load applied on the right side means only 40 kilonewton load will be applied at right side. So for section 1, load is decided, it will be tensile load and the magnitude of the load will be 40 kilonewton. So next we'll move for section 2. Here if you see the section 2, from section 1 far end at point B 40 kilonewton tension load were applied, but that at B for section 1 and section 2 face B is common. So whatever load is applied at section 1 at face B, in that reaction same force or load will be applied for the section 2, that is 40 kilonewton. Plus one more force is applied at the face B, that is given here 30 kilonewton, that incompressive in nature. So here that second load applied is 30 kilonewton, which is compressive in nature. Again we are going to sum up these two forces. So one is tensile 40 kilonewton and second is compressive 30 kilonewton, means tensile will be positive, compressive will be negative. So that net force will be 10 kilonewton, which will be positive. So this positive force will be 10 kilonewton, and this is tangential in nature. Okay, so whatever force is applying at the left side, right side also the same force will be applied. So for section 2, the tangential force will be applied, that magnitude will be 10 kilonewton. 10 kilonewton. So this force will be tangential force. So here this will be tangential force. So we can write tangential force. So this is decided, tangential force or tangential load. So this is decided. Then we move for section 3. So for section 3, if we move, what will happen? Here 10 kilonewton force is applied at phase C, because for phase C section 2 and section 3 is common. So while we are dealing with section 2, at phase C there was 10 kilonewton of tangential force or load is applying, and one more force, that is P, is applying at C. So here you can see in the figure that load P is applying, and that will be compressive in nature. That will be compressive will no, for section 3 it will be tangential in nature. So here we will see this load, so this will be tangential in nature. So what we will do, both forces is tangential in nature, so we are going to sum up. Then here you will get 10 plus P, that will be tangential in nature, and at the far end at point D 70 kilonewton force is applying. So this force will be tangential in nature. So what we will do next, here these two forces will be equal, because it's maintaining the equilibrium condition. So for that these two forces will be equal. So by making these two forces equal, P load P will be calculated 60 kilonewton. So one load P is calculated 60 kilonewton. So what next we are going to do? But finally here this load will be tangential in nature, and that magnitude will be 70 kilonewton. So again we will see the forces on sections. So for section 1, 40 kilonewton tangential force will be applying. So here that nature of force will be tangential only, not compressive. So this will take out, and the nature of the force will be tangential only. So we'll put the tangential load. Okay, so this is done. Now here the load at section 1 40 kilonewton, that will be tangential in nature. Load at section 2 is 10 kilonewton, will be tangential in nature. Load on section 3 will be 70 kilonewton, which is tangential in nature. So this is tangential force is applying. Here also tangential force is applying, and here also tangential force is applying. So this is done. So here now all sections are made up with the same materials. So for the same materials, that modulus of elasticity will be same. Now apply principle of superposition. What will happen? Total elongation is equal to sum of individual elongation for individual section. That will make a sum of these. So delta 1 plus delta 2 plus delta 3. As we know, elongation delta is equal to PL by AE. So as E is same for all, we will take a common 1 by E. Then load will be changing, P1 by L1. Load is changing, length is changing, area is changing. P1 L1 by A1 plus P2 L2 by A2 plus P3 L3 by A3. Next, here 1 by E is a common. Now P1 we have 40 kilonewton, so we will make it into the Newton. 40,000 into 600, that L1 length. Then 225 pi, if you will calculate, then you will get the area. So this will be the area A1, and likewise that area U2, and here the loads, tensile loads we are getting 10,000 Newton into 800 length, then 70 kilonewton means 70,000 Newton into 900 is the length, divided by 400 pi is the area for section 3. So here 1 by E into 86916, when we are calculating, we are getting this value. If E is equal to 2.1 into 10 to the power 5 Newton per mm square, suppose this is a mild steel, so this value will be nearly 2.1 into 10 to the power 5. For the sake of easiness, we will take generally 2 into 10 to the power 5 Newton per mm square. So what is the elongation? So total elongation delta is equal to, here calculated 86916.28. So this is 0.28. Let us make it 0.28. And 28 divided by 2.1 into 10 to the power 5 is equal to 0.414. That is the approximate 0.414 mm. So this is the calculation, how to calculate the loads. If the loads are different for different sections, then how to apply to calculate the total elongation. If different sections are added to make a single member, single solid members. So this is the procedures which we apply to calculate, to do the calculation. Thank you for watching. Subscribe and share this video.